Let's talk about the decibel scale. Now, the sound is measured using the decibel scale, but you may wonder, well, why use decibel? And why not just use Bell? Like, Bell was named after the inventor of the telephone, Alexander Graham Bell, originally used to measure sound intensity, but I think scientists found that bells were too rough of a measurement. So one bell indicates a tenfold increase in sound intensity, but maybe too rough. So imagine measuring something small like a pencil, and you're using meters. You would say, okay, well, the pencil is maybe 0.12 meters. But that doesn't really sound sensible to us. I think it makes more sense, and we can tell more differences if we said, okay, well, the pencil is 12 centimeters, because we have a better sense of centimeters. And I think that's the same way. To make better sense, scientists decided to divide each bell into 10 smaller units called decibels. And I have a little diagram here that we can show. So here we have the sound intensity graph where it's the same. These are all the same. And the Bell scale goes up by 1. And this is very similar to the Richter scale, where it's just each tick in the scale represents a tenfold increase, but a little bit too rough. So we decide to use decibels and split this 1-point scale into actually 10 pieces. And that we can maybe with some more precise descriptions of what the difference in sound is. So you have 1 decibel, which is a noticeable difference in sound, while a jump of 10 decibels is really just 1 point increase in bells, and that's a tenfold increase. So let's take a look at an example here so we can see. Let's compare sound intensity. So the proportion of two intensities, I2 and I1, can be expressed using the log scale as follows. You have I2 compared to I1 is equal to this tenfold increase, and then L2 and L1 are measured in decibels, and you may wonder, why are we dividing by 10? Now remember that decibels, we changed one scale in the Bell scale into 10 different sections, and so you could say that you have this decibel as 30 is actually the 0.3 on the Bell scale. So let's take a look at this example. We want to know how much more intense the jet engine, the sound of a jet engine at 110 decibels compared to normal conversation at 60 decibels. Well, using that formula, we can say, well, the intensity of, say, this jet engine, we use J here, compared to the intensity of the normal conversation, let's use C. And this is a tenfold increase when these are measured in bells. But remember that L2 here, this is in decibels, so that's 110 decibels. But in bells, we could say B, this would be equal to 110 divided by 10, so that'd be 11. And then the other sound in decibels is equal to 60, and in bells, though, that would equal 60 divided by 10. Now, according to the formula, if we were working in decibels, it would be L2 minus L1, and that would be in decibels. And then to convert to bells, we'd have to divide by 10. Some other students might say, well, let's just convert to bells and just use the tenfold increase. That would look like this. IJ divided by I over C is equal to 10, and just use the difference in bells, B2 minus B1. But if we're working in decibels, this would be the formula that we're using. It kind of ends up being equivalent. Let's say 10, so we have 110 here, 110 minus L1, which is 60, so put 60 in here, and then according to the decibel formula, we're going to be dividing by 10. If we were working in the bells, it would be equal to, well, using 11 minus 6. But it equals the same thing. We have 10 to the 50 divided by 10. And then that ends up being 10 to 50 divided by 10 is equal to 5. And we can see then the comparison of the jet engine sound compared to normal conversation is equal to 10 to the 5, which ends up being 100,000. So that means that a jet engine at 110 decibels is 100,000 times as intense as normal conversation. If you look at the Bell formula here, you could say, well, this is 10. 11 minus 6 is equal to 5. Again, you would get that 100,000. So you have a bit of a choice here. If you want to use the Bell scale, which is a little bit closer to what we use as the Richter scale, then you convert all your intensities into bells and then use the Bell scale that's more similar to the Richter scale. If you use the decibel scale formula, then remember that within the formula, it's going to create that equivalence to what the bell is. So decibels is 110 minus 60, and then you're dividing by 10 to convert to bells again. Okay, so that's it for decibel scale, and I'll see you in class.